everyone, welcome to Deeksha Vedantu. I'm your Aditi Mam, and in this video today we are going to dive into one of the most awaited chapters of your class 9th, that is exploring mixtures and their separations. Now I know how much you have waited for this new book, and this is the chapter that has almost completely changed. It's completely new. Some of the topics were there before, like solutions, the mixtures and all that, their types, but the separation part is completely new. Your seniors have not done it, and you will see maybe how interesting that is to learn all that. Some of the stuff I used to keep learning in physics masters, so you understand the depth of these separation topics, right? Chromatography, distillation, crystallization. And if you take even if you take engineering, if you take science field, you will see that you will be doing chemistry crystallization in your graduations as well. That's a really fun, and if you knew it beforehand, that's just cherry on the top. Okay, so now let's start this chapter with the very basic understanding of what mixtures are. That's the first question that will pop up in your mind, ma'am. What is exactly mixture, right? So mixture, beta, when you look at a sugar solution, you have water and you put sugar in it, right? Just before making chai, just before making milk, first we put water and we put sugar in it, right? Then tea leaves and all that stuff. Now that is what? That is a sugar solution, right? If you put salt instead of sugar, what is that? That's a salt solution. What is that? Salt solution. Air, there are lots of airs, right? Oxygen, nitrogen, hydrogen. What is this? These are all mixtures. In soil, in your soil, if you look, there are so many substances like nitrogen, like ammonia, and so much other chemicals, right? What are these? A solution of a mixture of chemicals, right? So all this includes under mixture, and the definition you are going to write in your exam is the combination of two or more substances held mixed physically together are called mixture. Done. Now, ma'am, why are we studying this, right? You will see that in a bit. Okay, I'll explain everything word by word in a bit, and for this chapter I can safely see, if you haven't opened your NCERT or if you just see this lecture, it's enough. To be honest, I don't say it, I say it that you read NCERT line by line, but this chapter, the way I made the PPT, it's not going to be any hassle for the exam to directly come from this PPT. Okay, mark my words. Now, so these are all solutions. Even your blood, even your milk, even you put chalk in a water, you put sand in a water, all those are what? All those are mixtures. What are those? Just substances mixed together physically, right? This physically word is important, you will see why. Okay, now bacha, these mixtures are of two types. Everything has types these days. Okay, do you have types? People have types. So what are mixtures? One is homogeneous mixture, another is heterogeneous mixture. Ma'am, what are you talking about? Homogeneous. So when you look at it, homogeneous, when you look at a mixture and you have, what do you have? Maybe you have a sugar solution, but you don't see sugar in it, right? The sugar is completely soluble in water. So what is that? That's a homogeneous mixture. Why? Why is that a homogeneous mixture should be your main question to me, right? Because it looks the same throughout. When you add sugar, because of the chemicals, because of something, the solution looks a little yellow, pale yellow, little yellow, right? And all the solution looks yellow. It's not like the upper part looks yellow, lower part looks white, or the whole solution looks a little bit of white, right? That it looks the same throughout. The whole glass of the solution looks the same. Done. Next, moving on to heterogeneous. Ma'am, heterogeneous, then just the opposite of homogeneous. It does not look same, right? It does not look the same throughout. So homogeneous, it means it looks the same throughout, and heterogeneous means it does not look the same throughout. Let's understand it a little bit deeply. I know. Okay, so first let's understand homogeneous mixture very clearly. Now you see, this is sugar, in water. Okay, now if you dissolve it completely, that becomes a homogeneous mixture. That means a mixture that has uniform composition. That means the partner, let's say the number of particles on the upper part of the glass is 10 in 10 ml of water. In the lower it will also be 10 in 10 ml of water. Everywhere you everywhere you pick, the number of sugar molecules in the water will be same throughout. Thus it has a uniform composition throughout, right? It's not like somewhere sugar is a lot, somewhere sugar is less. If you stir it completely and you drink it, it's not like first you'll get lots of sugar, then you won't get sugar. It's not like that, right? It tastes the same throughout. That means it's a homogeneous mixture. Then its components are mixed evenly, right? Its components are mixed evenly and cannot be seen separately. When the sugar is completely mixed, you cannot see sugar crystals differently than water, right? That's not the case because it's a homogeneous mixture. Understood? It looks the same throughout. If we're talking about taste, it tastes the same throughout, right? And they cannot be seen separately. These are the three main points of homogeneous mixture. Understood? Okay, beta. Now we have the examples that are sugar solution, same as salt solution, okay, and invisible to naked eyes. Done. Now moving on to heterogeneous solution. Now have you seen if you put some seeds in water, or let's say you put sand in water, is it a homogeneous? Can you see the sand molecules, the sand particles in the glass? You can see it, right? But if you can see it, it's not a homogeneous solution or a mixture, then it's a heterogeneous mixture. Understood? A mixture that does not have a uniform composition throughout. Its components are not mixed evenly. They are not mixed evenly and can often be seen separately. You can clearly see sand in the water. And that's what a heterogeneous mixture is. Done? Okay, now what are the examples? We have sand and water, we have oil and water as well. You can see oil differently from water, correct? And they are visible to naked eye. So basically a homogeneous mixture looks the same throughout, while heterogeneous mixture does not look the same throughout. Okay, my throat is a little bad, okay, so just be with me. Okay, now beta, we have seen mixtures. Now I'm again talking about solutions, sugar solution, salt solution and sand solution. What is that? What is exactly a solution, right? So bacha, when we talk about solution, we have two kinds of mixtures, homogeneous, heterogeneous. Now we are going to kick heterogeneous out of the chapter at this moment, for this moment. Okay, now a solution bacha will always be homogeneous. It will always be homogeneous. Now remember, how do you remember this? Ma'am, let's remember it in a chronological order, okay, in a pattern. So you remember heterogeneous, homogeneous. Now then we talk about solutions. Ma'am, hetero is something that does not look the same, homo is something that looks the same, and homogeneous is like it takes everything together. It does not leave sugar out, okay, but heterogeneous leaves the sugar out. So I'll keep the one that includes everyone, okay. So that's a homogeneous mixture. So solution bacha is a homogeneous mixture in which one substance dissolves in another substance. Now we talked about sugar solution. Now what is happening? Sugar is dissolving in water. Okay, you have this glass of water and you're putting sugar in, right? You are putting sugar in. So what you are doing? You are dissolving sugar in water. We don't say we are putting water in sugar. That's different. That means different, right? We are saying sugar in water. That's a sugar solution. So bacha, in solution we have two things. Okay, see, we talked about a glass of water, okay, and a teaspoon of sugar. Okay, and these are sugar crystals falling from the spoon. Then, and we have water. Now, can we clearly see we have two things? We have two substances. One is what? One is sugar, another is water. Okay, we have one is sugar and another bacha we have water. Now the substance that is more in quantity or that is being dissolved, that is getting the substance that is being dissolved. So sugar is something we are putting in the water, Correct. So sugar bacha is solute. Sugar is solute. Water in which we are putting the sugar. Water is something in which we are putting the sugar, right? So that is solvent. That is solvent. Now obviously the quantity of solvent, that is my water, will be more than solute, that is sugar, right? Let's understand, let's see the meaning. See, solute bacha is the substance that dissolves. Now what is getting dissolved? If I say sugar solution, will you say water is getting dissolved in sugar? No, you will say sugar is getting dissolved in water, right? I'm adding sugar to water and sugar is getting dissolved in water. So sugar, the one that is getting dissolved, is called solute. Okay, solvent on the other hand, the substance in which solute dissolves. The substance in which solute dissolves. So this is the substance in which sugar is dissolving in, right? So that is our water, this is our salt, or you can also write sugar. Both are same. Okay, then bacha we have solution, the final mixture, the final that sweet water you get, right? With sugar and with water, the final solution you get is your what? Solution. The final solution you will get is your solution, and the solution is salt plus water or sugar plus water. Understood? Up till now, up till here, I think it's very clear, it's very basic. Okay, now bacha, moving on, we have basically, let's see some examples. Okay, so a solution meaning a homogeneous mixture that is made up of solute and solvent. Solute is what? It's my sugar that is getting dissolved, and solvent is water in which sugar is, or in which solute is getting dissolved, right? If I have sugar solution, then solute is what? Solute is sugar and water is solvent. Water is solvent. If we have salt solution, then salt is what? Salt is solute and water is solvent. If I have lemon water, now lemon is this much. Few drops of lemon you put in water. So you dissolve lemon in water. So lemon is what? Lemon is solute. Lemon is solute, or you put sugar, you put salt with all that for taste, right? So your water is what, bacha? It is solvent. Now also remember, I told you that air is also a mixture, and air is a homogeneous mixture, because I cannot see, oh, this is oxygen, this is nitrogen, this is hydrogen. I cannot do that, right? All I see is a homogeneous mixture of so many substances, so many elements. That is air for me, right? Now bacha, in that air we do know that the percentage of nitrogen is highest. So can I say that oxygen is only few percentage, nitrogen is around 70%, right? So that few percentage of oxygen is being dissolved in 70% of nitrogen. So nitrogen is my what? Nitrogen will be my solvent, right? And gases like oxygen, like carbon dioxide, all these are what? All these are solute. Understood till here? Okay, great. Now bacha, we are going to talk about something very, very, very interesting. Okay, concentration of a solution, the amount of solute present in the amount of solution. Now see, we studied that this is a solution, and this is, let's say, my glass, and this is water, and this is 1 tablespoon of sugar. Now you tell me, 1 tablespoon of sugar in water, in the same amount of water, in 100 ml of water, will that be more sweet than 2 teaspoons of sugar in same 100 ml of water? Okay, so now you know what is a solution, right? And what is a solute, what is a solvent. Now you tell me one thing. I have 2 options. Okay, I have 2 options for you. One is, you like, okay, let's say you and your brother or your sister are sitting and you want to have some sugar in water for some reason. Okay, you want to have some sweetened water. So this is your glass and this is your sister's glass. Okay, and you ask your mama that, mama, put only 1 teaspoon of sugar in my glass, in this 100 ml glass, and I don't like much sugar. Okay, and your sister is like, no, I like sugar. Okay, so put 2 spoons of sugar in my glass, that is also 100 ml. Okay, now you tell me, you didn't choose this. Why? You didn't choose the 2 tablespoons of sugar because you know it will taste a lot sweet. right? That means the concentration of solute you are adding in a solvent, it makes its composition different, it makes its taste different. There will be more sugar particles in 100 ml of water than this case, right? It has less sugar particles in same 100 ml of water. So these two are very different, right? From there, bacha, we take a concept that is concentration of solution, right? Now you have a solution, there is a solute, there is a solvent. How much solute is there in your solvent? How much solution does it make? How much grams of solute? How much ml of solution? All that we are going to study in this concentration of a solution. Okay, now see very carefully. This definition is important, okay? So the amount of solute present in a given amount of solution. See, these words are very important because students gets confused between solute, solvent, solution, right? So what you have to do, you don't have to remember water. Just remember what you are putting and what you are drinking, right? You are not drinking simple water, but water is getting sweetened by sugar. So remember sugar and the sweetened water only. Okay, so the amount of solute, the amount of sugar that is present in a given amount of solution, that is sugar plus water, not just the water. So that amount, number of the sugar, number of teaspoons of sugar present in the complete solution is called your concentration of a solution. Okay, and we talk it in a language that makes us understand it better is how much solute is dissolved in a solution, how much solute is there in a total solution. We never say how much solute is in a solvent. No, we don't say that. We say how much solute is there in a solution. Done. Now, bacha, there are three categories, three types in which we can measure these concentrations. The solute in a solution, it can be measured using, now you tell me, when you buy sugar, you tell 1 kg of sugar, 2 kg of sugar, 10 kgs of sugar, right? But when you say water, you say 500 ml of water, 500 liters of water. So there are two things. One is your weight, right? And another is your volume, right? So we can measure our solute and solution and solvent using these two units, weight and volume. Done. Now, bacha, the very first thing is your mass by mass percentage. That means you take your solvent, that is your sugar, in kilograms, in grams, and you take your water also in grams. Ma'am, what you are saying? It is true. We don't measure usually water in grams or kilograms, but I can just get 1 liter of water and weigh it, right? It will give me some weight, right? And my water's density is 1. So it is almost equal. 1000 grams of water will be equal to 1 liter, 1000 ml of water, right? So, but we measure all solvents, all solutions in grams. So that is by mass. Solute and solvent both measured in grams, and we write it mass by mass percentage. Okay, done. Next, bacha, we have mass by volume percentage. That means solute is measured in grams. You are taking sugar in kilograms, grams, but you are measuring the final solution, sugar plus water solution, in volume in ml. So that is m by v percentage. Done. Understood. Next, bacha, we have volume by volume. Now this was mass by mass, this was mass by volume, this is volume by volume. Now you understand. You measure sugar in volumes. Ma'am, how will I measure sugar in volume? So it won't be used in sugar example, right? Maybe you sometimes add acid in water, right? You don't add acid in water. Okay, you add a lot, small water in your, I don't know about that. Ma'am, what you are saying? How will I measure sugar in volume? I can't go and buy 1 liter of sugar. No, you can't. But there will be lots of cases, beta, in which we add some liquid in another liquid, like lemon juice, right? So if you just squeeze the lemon and you take 2 or 3 drops out, you can measure that in milliliters, right? So you can measure if you want. If you are adding lemon drops in water, then we'll calculate by volume percentage. Okay, let's just look at some very important numericals. Now pay attention back to here. Numericals in this case, bacha, are very important. Okay, now read this very carefully. If 10 gram of salt, now in my class we read as we write, everybody knows. Now mass of solute. Now clearly we see that salt is a solute, right? Salt is a what? Salt is a solute. So mass of solute is what? 10 gram. Then is dissolved in 90 gram of water. So now bacha, remember, this is what? 90 gram of just water, not the solution. Okay, so mass of solvent. In this we'll have mass of solvent, not the mass of solution. Okay, if we have solution, then they'll give you that this is a solution. Done. So this is 90 grams. Done. Calculate the mass by mass percentage of the solution formed. Now we have to calculate mass by mass percentage. Okay, now look at this formula very carefully. Whenever you have to calculate mass by mass percentage, what you have to do? Mass of solute divided by mass of, remember, mass of solution. Okay, in your +1 you will also study few formulas in which you will, instead of solution, you will use solvent, right? But that is not there in your class 10th. Okay, now whatever the question gives us, we are going to stick with this formula, mass of solute by mass of solution, right? Mass of solute divided by mass of solution. Understood? Now see, I have to calculate this. What is the mass of solute? Mass of solute is 10 gram. Mass by mass percentage, mass of solute is, that is mass of salt, right? Mass of salt, that is 10 gram. Then bacha, we have mass of solution here, but here we have mass of solvent. Then what we'll do? Solution is what? Just the mixture of solute and solvent, that means salt and water. So if I just add these, will I get the mass of solution? Then mass of solution is what? It's mass of salt plus mass of water. Okay, understood? Now mass of salt is what? 10 gram plus bacha mass of water is 90 gram. So 90 plus 10, that will be 100 gram. This comes out to be the mass of solution. Done. Now I'll just put this value in my formula, right? This is 100 gram. Done. So this cancels out, this 10 cancels out. Mass by mass percentage comes out to be 1 by 10, that is 0.1%. And that bacha is your final answer. Okay, understood everyone? No doubt. Okay, let's see the second type of question, second type of solution, right? If 5 gram of glucose is dissolved in water to make 100 ml of solution. Okay, now pay attention. We have 5 gram of glucose, okay, dissolved in water to make 100 ml of solution. Now they have given us the volume of solution. Earlier they gave us the mass of just solvent. Okay, now that's the difference. So mass of solute, glucose is just solute, right? Mass of solute, that is your 5 gram. Understood? Now this is 100 ml. Is it mass or is it volume? Ma'am, this is volume. Correct. So volume of your solution, not your solvent, it's a solution. Your solution is what? 100 ml. Now we have to calculate is mass by volume. Pay attention to this. Look at this very carefully. It is mass by volume. Done. So we will write mass by volume like this, mass by volume percentage. And just like before, we are going to stick with solute and solution no matter what is given in the question. Okay, remember, okay, no matter what is given in the question, you will be stick with solute and solution. Done? But see, now it's mass by volume. So I will write mass of solute divided by mass of solution or volume of solution. It will be volume of solution. Volume of solution. Understood, bacha? Now remember that this formula is always from gram and milliliter. If you ever have kg, if you have ever liters, change it to milliliters and milligrams. Done? Okay, now we have all the things. Let me just put this in my formula. Mass by volume percentage, mass of solute, that is mass of glucose, that is 5 gram, and we have volume of solution 100 ml, so that is 100 ml. So this will be what? Mass by volume percentage is 0.05. Can I leave it here? No, this is the most important part in chemistry, and you will see what is the importance of this in your +1, +2. But right now, it's also very important, that is 0.05 m by v percentage. That is your complete answer. Okay, that is your complete answer. Here also, you'll have to write mass by mass. You'll have to write 0.1 mass by mass percentage. Okay, they will cut your marks, definitely half marks or maybe 1 mark even gone. Okay, so remember this. Done? Second question complete. Now move on to the last type of question. Let's just quickly see it and let's go to the next topic. Okay, now read carefully. If 1 ml of liquid pesticide, now liquid pesticide, so this is 1 ml, of course this is 100 ml, so 1 ml, 1 is solute, right, is mixed with a sufficient amount of water to form 100 ml of pesticide spray for rice crop. Now also bacha, they have used 1 ml of pesticide in water, in sufficient amount of water to form 100 ml of the final solution, the final pesticide spray, right? So here the volume of solute is given. Now you can see it's not about solution, it's not about sugar and salt every time. It is, this is actually solute, right? So this solute is this pesticide, right? That is 1 ml, that is your volume. Done? Solute is also in volume now. Then volume of solution is given. Solution is given, that is what? 100 ml. Now can you form the formula of V by V percentage? Calculate its volume by volume percentage. So volume by volume percentage will be what? Volume of solute in milliliters divided by volume of solution also bacha in milliliters. Understood? Now I'll just put the values. V by V percentage is what? V by V percentage is simply 1 ml divided by 100 ml, right? So this will be 0.01 V by V percentage. V by V. Understood? Okay, very good. Now let's move on to the next topic, bacha, that we have a very important one. Now see, we talked about solution, we talked about homogeneous solution, heterogeneous solution, right? So in that, bacha, we have a few more things, that is mixtures, right? Homogeneous mixtures, heterogeneous mixtures, the one you can see with your naked eye is the one particles that you cannot see with naked eyes, right? This is, bacha, this is solution. Okay, you have solution is homogeneous, we know that, right? There are some other particles, other kinds of solution as well, like milk. right? Milk is not completely homogeneous, and it does not look like sugar solution as well. It's not the whole consistency, right? Milk is some that milky substance, that cloudy substance, right? On the other hand, blood, now we know if you keep blood somewhere, it will somehow separate through a liquidy thing, but we cannot see cells as well. So what are all these things? That's why these things are classified into 3 types of solutions, right? First is but a simple true solution, right? Then it's a colloid, then it's a suspension. Now let's see what are those. Now see, let's look at the examples first. Example is sugar solution, salt solution, that is true solution. That is done. That means it's homogeneous. It looks like one, it feels like one, right? Feel it from your heart. Okay. Next, bacha, we have milk and blood. Okay, before that, this is sand in water, chalk in water. So these two you know. Now this is sand in water, chalk in water. This is called colloid. This is called suspension. Sorry. So suspension, bacha, it has bigger size of particles. If you see sugar solution, you can't see sugar. Why you can't see sugar? There is sugar inside the water, because the size of particles, the dissolved sugar has also particles, and that size is very small and can't be visible to naked eye, right? On the other hand, bacha, suspension, you see the sand particles are so big, the chalk particles are so big that you can see with your naked eyes. But there is something in between that you can see but you can't see. That is your blood. You cannot see particles like sand, but it's not mixed like sugar solution as well. That's milk. You cannot see particles like sand, but it's not mixed as well. Now that is bacha colloid. The particles of colloid, the particle size is somewhere between true solution and suspension. Okay, so these are the 3 things that you have to know, and you'll know why you have to know. Okay, I'll give you that as well. Okay, now bacha, see, solution, it's now we see true solution, we cannot see anything, so it's homogeneous, right? It's homogeneous. On the other hand, colloid, that is milk, that is blood, that is your heterogeneous mixture. You cannot call that homogeneous, that is your heterogeneous mixture, and suspension is obviously heterogeneous. Okay, now bacha, particle size. Do you have to remember this? Yes, you have to remember this. Okay, now see, this is nanometer. Nanometer is 10 raised to power minus 9 meters. You know, 1 meter, multiply that with 10 raised to power minus 9. It's so small, it's so small. And you know, particles of sugar are so small. So less than 1 nanometer, the solute, that is your sugar, that is your salt, that particle size is less than 1 nanometer, right? But their suspension, it has more than 1000 nanometers. The sand particles, the what do you call, chalk particles, all are greater than 1000 nanometers. Okay, now colloid, somewhere between them, 1 nanometer to 1000 nanometer. Done. Now one more thing you have to know from this, that in solution, bacha, we have 2 things, right? Solute and solvent. That is not the case in suspension and colloid. You cannot call sand a solute and you cannot call water a solvent, right? Because when we just started solution, what did we say? It's a homogeneous mixture, right? And sand and water is definitely not a homogeneous mixture, ma'am, right? So in that, we don't call it as solute and solvent. We call it as dispersed phase, dispersed medium. So just like solute, the thing that is getting dissolved, that is your sugar and salt. But here, that sugar and salt is not there. In blood, we have fat, we have proteins, right? Protein particles, RBCs, WBCs. So all those are dispersed phase, right? So the solute, the equivalent to solute is dispersed phase, and the equivalent to water, solvent, in which they are getting dissolved, is dispersed medium. Same for suspension. Understood? Okay, now visibility, of course in true solution it is not visible, right? The true solution particles are not visible, but in colloid also the particles are not visible. See, feel it. Can you see the particles of milk? Can you see the particles of blood? Can you see the red blood cells? No, you can't, right? So it's not visible. But can you see sand? Can you see sand? Of course, ma'am, it is visible, right? So that is visible. Next, but just settling. Now, if you keep the dissolved sugar in water and you just let it standing, will you see that sugar is settling down if it's mixed properly? No, you won't, right? Will you see salt settling down, the one that is completely dissolved? No, it won't, right? So it won't settle down, correct? And collide also, do you see blood or do you see milk settling down? No, it doesn't, right? So it will not settle as well, right? But if you keep sand in water, and you keep it standing for a while, will it settle down? Yes, ma'am, of course. We see that sand comes down, it gives the smooth effect and it settles down, right? So the sand in water, it settles down, right? Now filtration. Bacha, can you filter your sugar out of water? No, you can't. When you filter the chai patti gets filtered, but sugar, you still can taste sugar, right? So sugar can't be filtered out, so it won't filter out, right? Then also, when you filter out, not blood, I was going to say blood, no, don't filter out blood. But when you filter out milk, can you see milk particles different than water molecules? No, you can't, right? So it cannot be filtered. Obviously, sand cannot be filtered, right? Easy, right? Now coming on to Tyndall effect. Now, bacha, Tyndall effect. Let's study about it first. Okay. So, bacha, have you seen this kind of view? Somewhere, anywhere. When I was little, there was like a room on a roof and I used to sometimes sit there in like winters and all, and there was a small hole there. And when the sunlight, it used to come and used to illuminate the room like this. I could see the small particles flying around in that. I used to catch them, but I couldn't catch them because, I don't know, they were there, they were not. Now, of course, they were there. That's why I could see them. But what is happening there? I cannot see other particles where it was dark. I could only see the particles where there was sunlight, where there was light, right? So what is exactly happening? Now, bacha, you remember light, right? When you remember light, you somehow do remember that the light, we can see things because light bounces off them, right? You can see me because there are so many lights. If I turn off the lights, will you be able to see me? No, you won't be able to see me, right? Then why you are able to see me? Because light is striking me and then it's going into your eyes, right? Now, similarly, the case with particles. Whenever sunlight comes and it strikes those particles scatter light. Those particles scatter light. And because of that, it just does not look like a single particle, that this is the light. It came and it hit into our eyes. No, that's not the case. Okay, your beautiful eyes. That's not the case. Actually, what happens is this lights come. Okay. And this is the particle, it gets scattered in all the direction and some of the rays goes into our eyes. There is another particle, it also scatters so much light when this goes. So this is what exactly a Tyndall effect is, that due to the light, that light is scattered by the small particles, the colloidal particles, and because of that the beam of light, the path of light gets visible, right? This happens because light gets scattered, the dust and smoke particles in the air. Now, bacha, these dust particles, these smoke particles, they are not like sand, right? They are not like sand and they are not like sugar solution as well. So, what are they? These are the colloidal particles. So, when we talk about suspension, when we talk about true solution and colloidal particles actually show the Tyndall effect, whereas true solution does not show the Tyndall effect. And suspension also shows the Tyndall effect. Ma'am, how do you know? How do you know that it shows the Tyndall effect? Okay, I'll tell you how do I know. Now, there is this very good activity in your NCERT and it can come in your exams as well. Okay, now, if you can clearly see, we have a laser. Okay, we have a laser and we have a sugar solution. We have a sugar solution and this is now a true solution, right? This is a true solution. Sugar solution is a true solution. Now, whenever this light is passing, can you see any light inside this solution? Any light inside the solution? No, you can't see. You can just see this spot on the wall, right? So the path of light is not illuminated. The path of light is not visible, right? So Tyndall effect was what? Path of light becomes visible. So Tyndall effect is not shown. Done. Understood? Now look at this. Now this one is bacha. What is this? Look at this very carefully. See, the path of the light beam was not visible in solution A. The particles in suspension B scattered the beam of light, making its path visible. Now this bacha is a suspension. This is what? This is a suspension. That means either a sand solution or a solution of chalk in the water. Now clearly see, the path of light is little bit visible. It's not direct, right? It's not accumulated at one point just like this. I'll explain this to you, but here it's more scattered, like scattered, right? So this whole bigger spot is visible, not a single one, right? Then coming on to C. Now in mixture C, the path of light was visible, indicating that the particles scattered the light through the mixture appeared homogeneous, right? Now here bacha, even if you see, you can clearly see that this mixture is a little bit cloudy, right? This is very clear. This is not that much clear. This is very cloudy. So you can see it's not that clear. But still the path of light is little bit scattered. It's a little bit scattered, right? That is why bacha, that is because it's a colloidal solution where the path of light is visible and hence it shows Tyndall effect. In suspension also the path of light is visible, even a minute one, but it's visible. So it also shows Tyndall effect, right? And scattering of light occurs when it passes through a colloid or a suspension, but not when it passes through a transparent solution. Understood, bacha? Understood? Clear? So you understand now what is a Tyndall effect, from where it's seen. It is seen in suspension as well as colloid, and it is not seen in true solution. Understood? Okay. Now basically that's all it in solutions, and we'll move to the separation part very quickly. Just one thing is left, and that bacha is, you now understand, right? You know what colloids is. So medium sized particles somewhere between true solution and suspension, right? Neither they settled nor they are visible to the naked eye. What are the examples? The example is milk. The example is this blood sample, right? Here this is not blood, okay? This is something wrong with this image, but you see a clear thick fluid, right? You do not see your RBC, WBC flowing around. Done. And this fog, when you go in mountains or when you see the fog around in winters, all this is what? This is colloidal solution. Your ice cream is also a colloidal solution. You cannot pick each particle apart, but it's not a true solution as well, right? So their particle size is between 1 to 1000 nanometers. Just remember this. Now true solution is less than 1000 nanometers, suspension is greater than, and colloidal is somewhere between 1 to 1000 nanometer. Done. So they are too small to see but too large to dissolve. Neither they dissolve in the solution and neither do they can be seen with the naked eyes like the sand. Done. Now bacha, a very important thing, solubility of a substance. Now I'm talking about sugar adding in the water. I'm talking about salt adding in the water. And what do? You try adding one. I'll give you one activity. Okay, today if you can, if your mother doesn't beat you with chappal, then you can do one thing. Okay, go and ask your mother for lots of sugar and you take 100 ml of water, okay, and you keep on adding sugar and keep on stirring it on the room temperature for now. Keep on stirring it, you will see the sugar is getting dissolved. Then add the second, then add the third, keep on stirring it. You'll see after third or fourth or fifth, let's say fifth, you are very great, and fifth you'll see that sugar particles are not dissolving anymore. They goes in the solution, they goes in the water, and they settle down. They settle down, and you add more, you are stirring, but they're settling down, right? They're not getting mixed in the water. So what is that? What is happening? That is where the concept comes, solubility of a substance. That means, bacha, there will always be a maximum amount of sugar that you can add in a specific amount of solvent or water, right? So maximum amount of solute that dissolves in a fixed quantity of solvent is called its solubility. Now what did I say? At room temperature, at a given temperature. That means if you keep adding sugar, but if it is given that only 5 tablespoons of sugar can be added in 100 ml of water, then you won't be able to dissolve the 6th tablespoon of sugar, right? Because that is the solubility of that substance. Understood? Now, that basically means that sometimes we cannot add too much load on a substance. That goes with you as well. Okay, keep on adding little pressure on you. Keep on stirring. By stirring, I mean going out, talking with your friends, hanging out, right? And hence you will be able to take a little bit more pressure. Okay, now that was a little yarn out there in the form of chemistry. Now we have, bacha, 2 kinds of solutions. One, we have saturated solutions, another we have unsaturated solution. Now, do you know the word saturated? It's basically, we have seen it again and again and lots of time, Mom, saturated, I can't work more. That means you can't put more work, you can't put more information in your brain because your brain has reached a limit. It is saturated. It can't handle more, right? Just like that, when you put sugar in water, till 5th spoon water is like, I cannot handle more sugar, don't give me more sugar. And you're like, no, I will add the 6th one. And your water is like, okay, then your wish, you keep on adding, I won't even dissolve the sugar, right? So that is saturated solution. That has become, after 5 tablespoons, that solution, the sugar solution has become saturated. That means more solute, more sugar cannot be dissolved anymore. A solution that cannot dissolve any more solute at that temperature, this is very important, at that temperature is called a saturated solution. Done. Now we are doing that activity, right? Now what I want you to do, I want you to keep that same solution, the water and the sugar, on a burner, on your gas, right? And turn on the gas and now keep stirring it, and you will see the sugar starts to get dissolved in the solution. Now what is happening? Now the sugar is getting dissolved. Why or not the room temperature? That is where temperature comes in. Bacha, whenever you will see that you are dissolving a solute in a solvent, and as you increase the temperature, its solubility increases. What does? Its solubility increases with what? With increasing temperature. Now that is true for solids, that is true for liquids somewhat, but that is not true for gases. Okay, so what happens in solids, the molecules are so tightly packed, right? And in liquid they are still tightly packed, not that far away like gases, but they're still together, right? So when you start to heat the temperature, they start to vibrate and they accumulate more stuff inside them, right? That's the basic idea of it. But when you see gases, the gas molecules are already very far away from each other. When you give it energy, it leaves out that liquid, right? When you say Coca-Cola, you have seen Coca-Cola, right? Now, if that Coca-Cola is very chilled, right? So you'll get so many bubbles. But if you keep it out in the let's say warm temperature, in your normal temperature room, you will see, and you open it, you will see it has less gas. So why it happens? As the temperature increased, the molecules of gas got a good amount of energy and they left that liquid, they left that gas all along. So with the temperature increasing, the solubility of solids and liquids, they increase, but the solubility of gases decrease. Just here the points are mentioned. Now you are stirring that, you are still stirring that sugar solution, right? Now what is happening? Sugar is getting dissolved. Now what it became? It became a unsaturated solution. That means a solution that can dissolve more solute. It can dissolve more solute, and that temperature is called unsaturated solution. Now what you did was physically you forced the sugar with the temperature, you forced the sugar to dissolve in water, right? That became saturated. Now unsaturated solution, let's say you have just dissolved one spoon of sugar in that water in 100 ml, and there is still some leverage that you can second, you can put third, so that first the solution after the first tablespoon of sugar, that is unsaturated solution. Okay, done. Understood? So in saturated you cannot dissolve any more solute in the solution, and in unsaturated you can dissolve more solute in that solution. Okay, understood? Okay, now bacha, moving on to the next one, we have something like this. We have the solubility curve. Now I have told you again and again, okay, that whenever you see a solution, whenever you see physics or chemistry or even bio, you will see lots of graphs, and the sooner you understand, you learn to interpret them, the sooner it will be better. Okay, now solubility of curve, we will understand it in a very, very good way. You will understand it. Okay, now a graph of solubility versus temperature is called solubility curve. Okay ma'am, that's just theory, you just read it. Yes, I'll make you understand, don't worry. Okay, now see bacha, what happens here on this y-axis I write solubility, on x-axis I write temperature. That means, see what happens, this is compound A. Okay, this is compound A. Let's say sugar in a solution, that is my compound A, solution A. Now as I am increasing the temperature here, only let's say 25 gram per 100 gram water. That means 25 gram of solution was there in 100 gram of solution. I'm stirring it, but it's not getting dissolved. So I increase the temperature. Now the temperature is 10 degrees Celsius. Now you can see somewhat 35 gram of sugar can be dissolved in 100 gram of water. Now if I increase the temperature to 30, now 40 gram of sugar can be dissolved in 100 gram of water. I'm increasing, and now you see it's 60. Now 60 gram of sugar can be dissolved in 100 gram of water. Here only 25 gram of sugar was dissolved in 100 gram of water. Can you see the difference? So as the temperature is increasing, the solubility is increasing. Here you can only dissolve 25 gram in 100 gram. Here you could dissolve 60 gram in 100 gram. Understood? Now let's look at the compound B. Now you see this is more steep. That means what? That means when it was at 0 degrees Celsius, it could dissolve, let's say this is 180 gram of sugar in 100 gram of water. Done? Let's imagine some kind of sugar, right? Okay, then we are increasing where we see it is increasing slowly, right? It is increasing too much, and here it goes at 350. So now 350 gram of sugar can be dissolved in 100 gram of water. So how much distance this has? Difference this has 350 to 180. That is how much? That is more than almost 170. Right, almost 170, right? So bacha, that is how much the solubility increases. But if you see here 25 gram to 60 gram, that is only 35 grams. So its solubility increases by 35 grams, 35 units, let's say, and this solubility increases by what? 170 units. 170 units. So if someone asks you which of the compound can dissolve better with increasing temperature, as the temperature is increasing, it is also getting more dissolved. But out of A and B, which substance is getting better dissolved? That is your compound B, right? Correct? Understood? Now you can understand graphs. Okay, let's just read what is written here. Okay. The solubility of a compound A. Solubility of compound A in water at 20 degrees Celsius is less than its solubility at 60 degrees Celsius. Of course, the graph is going up. Here it only has around 70, not 70, 40. Here it almost has, 50, right? 40 gram in 100 gram of water, 50 gram in 100 gram of water. So that is more, right? Solubility is more. Correct. The solubility of compound B at 20 degrees Celsius. The compound B at 20 degrees Celsius is less than its solubility at 60 degrees Celsius. Again, it is 287 and here it is only 200, right? So, of course, the solubility is less at lesser temperature. Then, the solubility of compound B increases more than that of compound A with an increase in temperature. That's what I told you, right? Its solubility increases rapidly and its solubility does not increases that rapidly. It's slowly increasing, right? It is like getting a good jump. Then with the same increase in temperature, it also went from 0 to 80. It also went from 0 to 80, but it increased by 170 units. It increased by only 35 units. Understood? Then okay. Next, bacha, we are finally in the new part of this chapter. Now, before we dive into separation techniques, what are the specific separations? Let's just understand why separation of a mixture is actually important, right? Now, you tell me we eat pizza, right? But we don't exit out pizza, right? We exit some other stuffs. So what is happening inside my body? Separation is happening. All the minerals are getting separated. The water is getting separated. All the minerals from the pizza is getting, nutrients from the pizza is getting separated, right? Something you tell your heart to be happy, right? Now, what is my body doing? This is nature, right? And the nature is in itself has so many separation techniques, right? Now, also you can see there is so much dirty water right now, maybe in lots of our rivers, unfortunately, and we are somehow putting efforts to clean it. At least you are thinking about it, okay? So what we are doing, we are going to separate that all that garbage from the pure water. That then even if you like pick up all the garbage, you still see the water is muddy, it's sandy, it has so many chemicals in it. So we have to separate out those chemicals to actually use that water for something, right? So that is all that in nature where we use the separation techniques. Now in food industry, you also have to use these separation techniques, right? Just go into your kitchen and ask your mama, and when we boil the milk and we keep on boiling, what happens? It gets lower in concentration. Why? Because all the water is getting evaporated, so water and milk got separated, right? So it is used in food industry. It is used in power, water purification, medical diagnosis. When they take a blood sample, they didn't just measure all the blood, right? They pick up some parts of the blood when they calculate the RBC count, WBC count. So they have to somehow separate blood from that watery substance in the blood, the plasma, right? So that is all the things where we need to use these separation techniques. Ma'am, but I am in class 10th. Why should I study? Class 9th. Why should I study? Are you going to be in class 9 for your whole life? Somewhere you are going to be an engineer, you are going to be going to MBBS, you're going into research, all these preparation techniques will be used. Okay, do not worry. Now, let's understand what are separation techniques. Now, bacha, we have few methods of separation. Before that, we studied two types of mixture. That is homogeneous mixture and heterogeneous mixture. Okay, just give me 1 second, beta. Just give me 1 second. So, we have two kinds of separation. That is your homogeneous separation, and one is your two kinds of mixture. That is homogeneous mixture and heterogeneous mixture. Now, beta, when we talk about separation, of course, we have to use different method to separate water and sugar than to separate water and sand. You can simply use a very small filter paper to separate water and sand, but you cannot do that with water and sugar, right? So we will see them differently as well. There is homogeneous mixture, heterogeneous mixture. There are few kinds of these things. These words are a little bit scary right now, but stay with me. It is very easy. First is crystallization. As you can see from the words, it has something to do with crystals, right? It has something to do with crystals. Distillation, let's say a part, not a part of, but what do you say? rather a continuation of crystallization, okay, or a somewhat crystallization. Then we have paper chromatography, a very, very interesting technique. This you can definitely do in your house right now. Okay, now we'll see all that as well. Okay, now moving on to first bacha, what is crystallization? Crystallization bacha, basically we are going to work with crystals. What are crystals? If there is a random glob of some rock, will you call that a crystal? No, actually bacha, crystal is a solid, okay, that is for sure, but it has a specific arrangement of atoms, a specific arrangement of atoms, molecules in a regular geometric pattern. If you see, this is not that specific if you call this as a crystal, but this is also a crystal, it has its own pattern, right? You see these small granules, these are what? These are crystals. If you see, if you have been to somewhere where it snows, you will see that on the window cracks of your car, you get snowflakes like this. You get snowflakes like this. So crystallization is already happening in nature around us. It's already happening, right? We just have to use it for our favor in some way or the other. Okay, so bacha, basically the process to form these crystals, we also form crystals in laboratory. So the process forming crystals from a saturated solution. Now this is very important, a saturated solution. What was a saturated solution? That we cannot add more solute into that solution. That is saturated solution. It has reached its limit. It has been saturated, okay, with so much pressure. Okay, in laboratory is called crystallization. Understood? Understood? So bacha, I have written all the steps here. Okay, don't worry, this whole steps here. But what we have to understand first is, what is the basic understanding of crystallization? Okay, now bacha, there will be two kinds, two types, two ways in which we can form the crystals. Let's say I have a solution, okay, I have a solution and I have some kind of salt in it, okay, a salt and a water solution. Now first case is I can evaporate water. I can evaporate the water. Now it's a saturated solution. No more salt can be added into it. That will get dissolved. It will settle down. But right now it's a pure solution. It's a homogeneous solution and you cannot add more salt to it. Okay. Now what I can do? I can decrease the amount of solute, that is water. Now if I decrease the amount of solute, you tell me, it's already a saturated solution, no more amount of salt can be put. But if I take out the water, not the salt with it, I evaporate the water, only the water will evaporate, the salt will not evaporate. Then what will happen? The concentration of salt in that whole solution will increase, because see, first I have 5 gram of salt in 100 gram of water. Understood? I evaporated. The volume of the amount of water got lessened. Now I have 5 gram of salt in what? In, let's say, 70 gram of water. Now this was already a saturated solution. If I take water out of it, what will happen? The salt will start to settle down. And that settled down salt, bacha, if you filter it, if you let it keep, we'll study what the process is, then that salt will form crystals. Done? Okay. Now second bacha is basically a rather interesting technique. So what we do, we make, let's just study about it. Let's study the steps, okay? And then you will see the second technique, because first was a little easy. Second, let's study about it. Now what you have to do, see, you have a beaker, okay, and you have taken copper sulfate solution. And you're adding more copper sulfate to it until the point it becomes a saturated solution. Okay, now what you do, you filter it with a filter paper. Okay, you will do it in your classes, labs, don't worry. So you take a filter paper, a conical flask, and you filter that copper sulfate solution. Okay, now what will happen, you will see some of the substance might get out in the filter paper. Okay, but there is a solution, and in that you will see some of the copper sulfate, some of the flakes. Okay, the filter it. Now if you let it settle down, and maybe we do it for the whole night, okay, so if you let it settle down, it form crystals like this in watch glass. This is a watch glass. It's made of a petri dish kind of thing. It's made up of glass. So let's study, let's read it out what is happening. Okay, see, collect a sample of copper sulfate. Then if copper sulfate is unavailable, use common salt as an alternative. So you can also do that. Then now take 1 gram of copper sulfate and place it in a 100 ml beaker. Then add 25 ml of water to the beaker. The beaker is 100 ml. There is no water. Water is only 25 ml. You add 25 ml of water, 1 gram of copper sulfate. Then add a drop of dilute sulfuric acid. Beta, why is dilute sulfuric acid added? So see, sometimes or a lot of the time salt can react with water. Okay, NaCl can react with H2O, it can form NaOH, right? So what happens is, to protect that, we add dilute sulfuric acid. It protects to keep them away. Okay, now gently heat the mixture in a water bath. Now if you have seen a water bath, you have seen there is this, it's a kind of a plate, okay, bowl. So in that, you don't place the beaker directly on the flames. Okay, you place it in a water bath. It's like kind of a bowl. You put water in it, and inside that you place beaker. So as the water gets heated, the substance in the beaker also gets heated. Okay, now as you put water bath, it's getting heated, right? You're stirring it constantly. Sulfuric acid helps in making pure crystals by preventing unwanted reactions. Understood? Now bacha, gradually add more copper sulfate until the solution becomes saturated. So until the 3 steps, we are just making a saturated solution. Now the actual step starts. Read it carefully. Filter the hot solution to remove insoluble impurities. Okay. Collect it in a clean beaker and cover it with a watch glass. So what we did, we filtered it out. All the insoluble impurities we took out. And this beaker we covered it with a watch glass, okay, and used it as a lid. Okay, now bacha, allow the solution to cool slowly. You don't just put it in a freezer and say that it will cool slowly. No, for the crystals to form very pretty, there are pretty crystals, there are bad crystals. We used to fight whose team will make good crystals. So there are pretty crystals, so you let it slow down, you let it cool slowly for the whole night, just on the room temperature. Do not put in a freezer or a fridge, okay, without disturbing it. And you don't have to disturb it. Also, you'll see, when you carry that beaker, your teacher will say, walk very slowly, walk very slowly. Do not even shake the beaker. That's how careful you have to be. Okay, it gives enough time the particles of the solution to come together. Now what happens when this saturated solution, it is being filtered out. Okay, now it's boiled, right? We've boiled it, we have saturated, made a saturated solution. Now beta, we filtered it. Now it is boiled, it is letting cool down very slowly, so that the particles that are in the solution, they can bound together. They can bound together and form the crystals to come together, resulting in the formation of larger, shiny, well-shaped, blue-colored crystals of what? Copper sulfate. So it is a process to remove the impurities and get pure copper sulfate solutions. Done? Filter the crystals, rinse them well with cold water. Now they have become globes, right? A crystal. So now you can wash them with cold water, not so harshly, and allow them to dry on a watch glass. Understood? Understood the concept of it, how we did it? In first, we cooled it down, we let it cool down. In the previous, we evaporated the water, right? So this whole thing makes sense now. Done? Okay. So the process of forming crystals from a saturated solution in the laboratory is called crystallization. It only is used to separate homogeneous mixtures. Okay, it is used to separate homogeneous mixtures, and also this whole activity requires very good safety. Okay, copper sulfate is toxic. Perform the experiment under adult supervision and do not touch with bare hands. Done? Okay. Okay. Now, bacha, let's move on to the next thing. Okay, we have a chapter in our new books like Think as a Scientist. So I have gotten you this. First, let's look at these. These are the naturally made crystals. These are naturally made crystals in where? In a cave, the Mavswami cave. Okay, it's in Cherrapunji, and this is just a picture of quartz. Quartz also a crystal. Okay, now if a hot saturated solution of copper sulfate is cooled rapidly in ice cold water, smaller and less well formed crystals will be formed, and if it is cooler slowly at room temperature. So again, if you put it directly into the fridge, a bad shaped crystal will be formed. Okay, done. Now bacha, you have seen that we did crystallization. What we did, we separate pure crystals from the impurities. Now let's say I am calling this as impurities, but let's say there is a sugar and a salt and a water solution. Now how can you separate that? Maybe just evaporate it. Evaporate the whole water and we'll get the salt. Now, but what happens is, maybe I need that water as well. If the water is getting evaporated, but I want that water to get liquefied from that steam and I want to drink that water. Can I be able to do that? That is the process of distillation. Okay, that is the process of distillation. Bacha, and what happens in distillation? See, it's a very crazy process. Okay, now if you see, it's a lot of text. It's actually not. This is just the example. Now, bacha, what happens? A homogeneous mixture of two miscible liquids. A homogeneous mixture of two miscible liquids. Okay, the liquids that can be mixed together, that are not separated, that are homogeneous. Okay, can be separated by heating. We told that we heated the water, right, until the liquid with the lower boiling point vaporizes. Now I talked about salt and water. Let's say we have two kinds of liquids only, maybe one acetone, one water. Now both of their, see, distillation is based on the phenomena of boiling point. It's based on the formula of boiling point. Done. Now what happens in boiling point? Why it is based on boiling point, bacha? See, if you have water, if you have acetone, then one will boil. We have boiling points of each the liquids, each the solutions are different. Water boils at 100 degrees Celsius. Maybe acetone does not. Maybe it requires more temperature to boil or less temperature to boil. So I'll just heat it. I'll heat it. As soon as the temperature reaches 100 degrees Celsius, water starts evaporating, and I'll keep the temperature at 100. So it is evaporating, but acetone is not evaporating. It is not evaporating. However, it's the opposite. So let's say acetone is evaporating, but water is not evaporating. So okay, acetone is gone and water is there, but I needed this acetone, right? So what will I do? I will use distillation technique, right? The vapor, the acetone vapor that went up is then cooled, because these are hot, that's why they are vapors. They are then cooled, right, turning them back into liquid. That is distillation. Water and acetone are boiling, acetone vaporizes, but I don't let it go in the temperature. I collect it, I hold it, collect it, and I cool it with something, and then it vaporizes back. Okay, it turns back into the liquid. Done. Now bacha, this is just a very important or cute thing I found about our India in the new NCERT. So I thought I'll tell you. In Kannauj, Uttar Pradesh, that is a perfume capital of India. Okay, so you know that I love that fragrance of the soil after the rain. So what they do in there, they collect that they actually make a perfume out of that very good fragrance of rain, right? And that is called mitti ka itra. We call it itra, right, in Hindi, so it's called mitti ka itra. They actually make it there. And how do they do it? They use traditional distillation method known as deg bhapka. Bhapka in Hindi is like what do you say, a cloud of vapor. So they use distillation to fetch that smell of that mitti, that sand after the rain, and they collect it in a bottle and they then sell it to us. Okay, so let's study it. So basically liquid is vaporizing, and again we are cooling it, and again the vapor is getting converted back into liquid. Now how exactly is this happening? So see, you have this whole beaker. This is a whole setup. Okay, you have this whole beaker. You will make experiments apparatus and you learn what exactly these are called. Okay, so now you have these burners in your lab. Okay, you have this wire gauze and you place a beaker over it. Okay, now you won't place it directly over the flame. There will be a thing here and it will be in the air. Okay, now bacha, what happens, instead of this water directly going into the atmosphere, we are doing what? See, let's say in this we have two liquids. One boiling point is 100 degrees Celsius, another is 150 degrees Celsius. So what I'll do, I'll reach the burner to, I'll take the burner just to 100 degrees Celsius, so that this first liquid evaporates and the second one, it does not evaporate. Understand? This second one does not evaporate, and the one with lower boiling point, it starts to evaporate. Now this is just floating in the liquid. The one first is evaporating, it's making vapors, but instead of going into the environment, we catch these vapors through this tube. This tube is called what? It's called water condenser. So what happening, there's a long tube, and inside that tube there is another tube. Okay, and outside, see, this is something like this. So this is a tube, and inside that we have another tube, right? And all this whole part is covered with water. This whole part is covered with water. Now from the inner area, liquid is that vapors are passing, and if now vapors are passing through the water, of course it's going to cool down the vapors, and then vapors will be converted into liquid form, and in a conical flask we will collect it. So it's acetone. There is acetone and water. We evaporated it. Acetone evaporated first, it went into this chamber, that is your water condenser, and with an outlet we connected this acetone here, and here the water is still remaining. Done? Understood? Easy? This was easy. This was not tough, right? So it's very easy. So let's study it. During the process, vapors of lower boiling point liquid, that is what? Your acetone. That is your acetone. Right? Are passed through a condenser where they are cooled, usually by circulating water or air, and condensed as a pure liquid. Air, beta, you have seen we use dry ice, right? That is also kind of air. That is also kind of a gas. So if we can use that as a condenser as well, that is why do we call it dry ice? Because it's very, very cold. So if we pass our vapors through dry ice, not in direct contact, these are not in direct contact, you can see, right? This is connected with that flask and this is connected with the water outlet. So the water is just around it, it's moving around it, and inside it is completely separated from water. But it is both the cylinders, both the glasses are in contact, so water is cool, so the vapors also get cool, right? So that we can also use a air condenser as well, right? The pure liquid is collected in a separate vessel, while the solid or other liquid from the mixture remains in the distillation flask. Done? A mixture of acetone and water can be separated by distillation because the boiling point differ sufficiently. Acetone boils at about 56 degrees Celsius, where water boils at 100 degrees Celsius. So if I just keep my temperature at 60 degrees Celsius, water will not boil. Acetone will keep on boiling, will collect it, pass it through water condenser, and collect it in another glass. Now we have water and acetone differently. Done? Okay. Allows one liquid to vaporize before the other vaporize. The liquids are formed in significant amount. Done. Now one thing you have to take care of, bacha, in distillation, these are only separated if they have a difference in temperatures of 25 degrees Celsius. See, if acetone has the boiling point of 90 degrees Celsius and water has a boiling point of 100 degrees Celsius, then you can't use this method. Okay, these both two liquids that needs to be separated should have a difference of 25 degrees Celsius in their boiling points. Done? Now, bacha, after distillation there comes a term called fractional distillation. So fractional distillation is basically, it's a process of separating the components, okay, of a mixture with relatively small differences. Now we studied about distillation can only happen if the difference is 25 degrees Celsius, right? But fraction distillation, if something does not have 25 degrees Celsius difference, then what will we do? Then we'll do fractional distillation, right? And that is how bacha we separated petrol, diesel, aviation fuel, petroleum gas using this fractional distillation. Okay, so what do you have? You have this big chambers. You have big chambers. Till here the boiling point is 100 degrees Celsius, let's say, but here the boiling point is more. Okay, here the boiling point is not more, it will be less. Okay, so if you boil, let's say you have whole oil here, lots of oil here, that is crude oil. So crude oil comes, there was lots of news about crude oil. So what is happening? What is crude oil? Crude oil, which is a mixture of all this, the petrol we use, the diesel we use, the LPG we use, the aviation fuel we use, like. Now what happens, when you send this crude oil into this furnace, there is this temperature and this crude oil boils, the one with lesser boiling point, it boils, it goes up, and here we collect bitumen, right? Then here goes, and now the temperature is little less. Okay, now the liquids which have lower boiling point, they again boil, and here we collect the lubricating fuel. Again lots of mixture, the ones with have lower boiling point again boils, and here we collect diesel. Again the same, the water with the mixture with less boiling point again boils, again vaporizes, and we collect here the aviation fuel, and then we collect here petrol, and at the last we'll get petroleum gas, that is our LPG. So on levels we are vaporizing the substances with different temperatures, and we are collecting them at every point wherever we need them. Done? Okay, so fractional distillation is the process of separating components of a mixture with relatively small differences less than 25 degrees Celsius in their boiling points. The gaseous fraction is filled in steel. Okay, these are steel cylinders under high pressure where it gets liquefied. It is used as, what is this? I don't know. Okay, just ignore it. Okay, so it's a steel chamber, and all these gases, these are boiled and then they are collected, and there's so much pressure on the gas. You have this beaker, there is so much gas. If you apply pressure, it will liquidify. Okay, the molecules will come close, right? Gas molecules are so far away. If the molecules come close, they will form a liquid, and that's exactly what happens here. Okay, then we are vapors, we have to come get them back as liquids, right? So either we condense them or we apply lots of pressure, then also they condensifies into liquid. Done? Okay, bacha. Oh, next we have Deeksha Vedantu. What is it? It's written paper chromatography. You have seen this? You have seen this phenomena. If you write something down with black pen, blue pen, when you are like so writing down in your exam, at the end moment teacher come, give you the paper, and you're so sweaty, right? You are sweating because you might not know the exam, right? And the tap, and the paper and that pen is like getting this kind of structure. Okay, it's leaking and all. So what is this? Okay, this actually is not paper chromatography, but this is how paper chromatography is. Now bacha, paper chromatography is a process in which we separate the components of a mixture by using a paper and a technique which is very interesting. You can do that. Okay, what do you have to do? Let's see what we are doing first. So we are taking a paper. Okay, we are taking a paper or a small paper strip, rather a small paper strip. Now take a black pen. Let me just add this. This is whole a white paper. Okay, let's say white paper for you. Let me just make a white paper. This is a paper. Okay, now let's say this is a white paper. Done. Now what I want you to add one line here, mark one line here like this, and then over that just mark a big drop of with your black pen. With your black pen, make a dot like this. Understood? Make a dot like this. Something it will look like this. Now take a beaker, any beaker, take a glass, any beaker, and you have to dip that strip inside the water, but the water level should not reach here. The water level should only be till here. This should be your water level. The strip should be barely touching the water, okay? The dot is here and the water level is way beneath the dot. You can look, the dot is here and the water level is way beneath the dot. Right now, what will happen? You will see that obviously inside the water, inside the paper, water keeps rising, right? Even the part which is not dipped in the water, it will get wet, right? And with that, in that way, we have this dot. So what will happen? This dot, the water will keep on rising, and first you will see it is very dark here, then it will become light, then it will become lighter. At some point you see that you used a black pen, but you can see up till here you will see blue marks. So that means your black pen is made up of blue ink. It's made up of a mixture of things, right? Blue is one of them. Okay, so what happens is, in this we use differences in the interaction of components with the solvent and the paper to separate them. Now see bacha, if there is an ink and it has love towards water, so it will say, okay, bye, I'm going with water. So it will go up with the water. But there are some molecules that are like, we are very loyal to the paper, so I'll stay with paper. So some of the mixtures, the components of the mixture, they will stay here, they will stay with the paper, and the rest of the components, they're like, they want to be loyal with water, they go up with the water. That's how we define affinity of a substance with either water, that is your solvent in this case, it can be something else, or affinity of that substance with paper. If it has affinity with paper, it will stay here. If it has affinity with water, it will go up with water. So basically what we do, we take the use of that affinity, that interaction of components with the solvent, that is your water, and the paper to separate them. And we are like, you do you. Whoever you have affinity with towards, we just want to separate you guys. Okay, so we use paper chromatography. You'll remember this? Okay, the liquid carries the substance up the paper, separating them based on how fast they move. Done. That is what your basically a paper chromatography is. Now actually bacha, this is used in real life. If you see, you take a leaf and you want to see what are other substances or mixtures, components it's been made up of. So what you say, you'll take a leaf extract and you place it on a spot on a paper. Done, you did it. You put that in a solvent. Now this solvent cannot maybe be water, it can be something else. Now paper strip placed in solvent, you'll write, not water. Okay, and as this solvent rises us up through the paper, you'll see first you'll have a dark, that is chlorophyll B, then you have a lighter spot, chlorophyll A, then you'll have a rather mix of dark and green and yellow, that is your xanthophyll, then you'll see a yellow spot, that is your carotene. Right, so what is that? The carotene has more affinity, can I say it has more affinity towards what? Towards this solvent, right? But this chlorophyll A has more affinity towards what? It has more affinity towards paper, or this, yeah, towards this paper. Done. Understood now? With this example you understood. Okay, and these pigments, these leaf pigments are separated by paper chromatography. Done. So we can also separate different pigments present in the green extract of spinach leaves or colored pigments from the flowers as well. In some cases you may need to use a different solvent such as alcohol or a mixture of solvents. So solvent also has to be water. It's not necessarily all the time the case. Done. Okay, so basically these are the 2-3 ways in which we separate homogeneous mixtures. These was homogeneous mixtures. Now moving on to heterogeneous mixtures. What are separation of two immiscible liquids? We talk about miscible liquids. They collide, they are living together, they have no problem. But there are immiscible liquids. Have you ever tried to like dissolve oil in water? Can you? If you are a superhuman, you can. But you can see it takes small droplets. It takes the form of small droplets. And if you let it just be still, you'll see that the oil rises up and forms a layer like this. The oil rises up, forms a layer, and under that we see lots of water. Now, how do you separate these, ma'am? How will I separate one liquid from another that are not miscible, right? So that is pretty basic experiment. Okay, what do? You use this laboratory stand and you use this holder, right? So what you'll do, you'll see that this is kind of a flask, and but this is like you can open this and you can close this. So what you do take this mixture, the oil is on the up and the water is all the down, right, on the downside. So you'll open this valve and you'll see water will drip from here. Here the water will start dripping and you will start collecting the water. Till you reach here, all the water is mostly done, right? So you close the valve and then again you will take another valve and then you open it and maybe a small amount of oil will come out with that, right? And then you again close it. Now the oil is in this, all the water is drained, the water is all in this flask, all the water is drained. So you have separated oil and water. Easy. This was very easy. Okay, so the oil and water form separate layers. They do not mix and called immiscible liquids. Similarly, sand and water do not mix, nor do iron fillings and sulfur. So you can use these with the help of this technique. All these are heterogeneous mixtures. You have studied how to separate iron fillings from the sand, right? Using the magnets. That was solid. This is just liquid, right? That's the only difference. Done. Okay, next we have sublimation. Now, ma'am, what is sublimation? See, these are very easy. I'll give you a 1-page short note of all this to remember. Okay, or you can make one for yourself. When you give it to me, I'll give it to everyone. Okay, I'll give it to you, don't worry. Okay, this is a sublimation. Now, acha, we have again this flask. Okay, and we have a solution. This solution is mostly solid state, okay, or the something that sublimates. What do you mean by that, ma'am? Sublimes. What do you mean by that? Now, have you seen naphthalene balls, camphor balls? You know, they don't convert into liquid. They directly go from solid to gas. Solid to gas. They skip that liquid stage. So we are going to use that. Now, let's say I want to separate china dish containing camphor and sand. So I have accidentally mixed camphor powder and sand. Okay, now I want to separate them. Now what will I do? Ma'am, I will sit there and take each grain out. No, you won't do that. Okay, you have to go play your Free Fire and PUBG as well. Okay, now what happens, bacha? You take them in a flask, that whole sand and camphor solution. You take them in a glass and you start boiling it. See, this is a china dish, you can clearly see, right? So you start boiling it and this will get hot. Now what will happen? Camphor will directly convert from that solid mixture to vapors, right? But now this is not going out. I've covered it with cotton plug, so these vapors can't go out. They can't go out. So what will happen? This camphor will start sticking on the walls of this beaker. It will start sticking on the walls of this beaker, and once all the camphor has gotten on the walls of the beaker, we'll turn off the burner and we'll scrape all the camphor from the beaker's walls, and the sand is and the camphor is now separated. Done. So camphor on heating below its melting point. Below its melting point, we talked about boiling point, but now it's melting point. If camphor melts, that's of no use, right? It melts inside sand, no use. So we have to give it less temperature so that it does not melt, right? Changes directly from solid state to vapor state without passing through the liquid state. This process is called sublimation. Okay, now on cooling, vapors condenses back into solid without becoming a liquid. That's the one thing we take advantage of camphors. When we cool it down, it goes back to solid form and not to the liquid form. It skips the liquid form completely. This is called deposition. Now the camphor will get deposited on the walls on cooling, right? That's called deposition, going from vapor state to solid state. Hence camphor sublimes and separates from sand, because sand does not sublime on heating. Do you think sand evaporates on heating? No, but camphor does, right? So it sublimes. You can't say evaporate, but it sublimes. That is, it converts directly from solid to vapor. And when we condenses the vapor down or cool those vapor downs again, it again becomes vapor to solid, skipping the liquid form, right? And that solid is collected separately. Done? Okay. Next, bacha, we have alloys. Now, ma'am, what are alloys? Alloys, bacha, is like a mixture of two metals or non-metals. Okay, we have metals, right? We have non-metals. If you mix them together, they are alloys. How are they exactly made of? See, you can melt the metals, right? You have seen those hot stuff melting and beating to give it forms, malleable, ductile. We all studied that, right? So, if you melt aluminium and you melt another metal, let's say iron, and you mix them, you melted them, right? Now they are a liquidy form, another state, and you mix them and you give them a shape. Now they are not iron and not aluminium separately. Now they have become something, a mixture of aluminium and iron, that is called an alloy. And they cool down, they again becomes solid. So, when metals are melted at high temperature, they can be mixed together to form a solution. When such a hot mixture of two or more metal cools, it solidifies into a new material that appears to be a single metal. What are some of the examples? Bacha, brass, 80% of copper, 20% of zinc. Bronze, again 80% of copper, 20% of tin. And stainless steel, usually a mixture of iron and other elements like carbon, chromium, nickel, molybdenum. So all these when mixed together makes stainless steel. We see so many ads of stainless steel utensils, right? So what is that made up of? That's made up of iron and carbon, chromium, nickel, molybdenum. Done? Okay, this is very important. You have to remember this. Not that hard, not the composition, but just the elements of stainless steel. Done? Okay, next bacha, we have suspensions. Now, what are suspensions? Now, see, we have studied about homogeneous, heterogeneous. Now we are studying about heterogeneous mixture. Okay, in suspensions are bacha, see, these are solid particles like sand. Okay, they do not dissolve but remain suspended. So you have this solution and you'll have massive sand particles and it settles down. So it's a mixture and sand is settled down, all that stuff. Okay, that is another thing. But let's say you filtered it and you filtered all the massive sand particles, but still you will see that there are still some particles roaming around in this solution, that no matter how much you filter out, they are not getting filtered, right? There is some cloudy substance, there is some substance that is just in that solution that is not getting filtered out. So how to filter that one out? These are called suspensions. They are just suspended in the liquid. These are called suspensions, and we'll use mostly two techniques to separate these out. First is coagulation, that is coagulation, and the other one bacha is centrifugation. Where have you heard the word centrifugation or centrifuge or centrifugal force? You have heard that about, right? Now, bacha, this suspension is what is written. In case of suspension, the particles of the undissolved substance are larger in size than the particles present in the solution. So basically, of course, we can see the suspension, so it's larger in size so that we can definitely see it, but not that large so that it gets filtered out. Right, now what we do bacha, first is your centrifugation. Now have you done this? Like in we call it kikli in Hindi, in Punjabi also we call it kikli, kikli kavirdi, and something, there's a song when you sing while doing this. So what you do, you hold someone's hand and you start rotating in these circles, and do you feel a push outside? You feel a force, a push outside, right? That is what? That is a force acting outwards when you are rotating in circular motion. When you are rotating in circular motion, there is a force acting outwards, right? And as soon as if you leave their hand, you know you will go and you will fall back, right? Because there was a force. Now, see, this process involves is similar to this. It's a spinning of mixture in a tube at a high speed. Now, bacha, we have these machines with us, right? These are machines, centrifuges. Now, what will happen? They have these kind of tubes. They have these kind of tubes. Okay, these are tubes. The test tubes you have seen in chemistry lab, right? Now you put a solution in this, and when you cover this, when you press on, you will see that it will start rotating. You won't see outside, but it starts rotating on such a massive speed that it resembles this motion. It's rotating in a circular motion. Now what happens when the whole of this happens? These tubes, these are now like vertical, but what they do, these does not remain like this. These goes horizontal. When you close this centrifuge, when this starts to operate, these tubes, they get horizontal, and now they are rotating in this kind of direction. So what will happen? A force on the outside side will act on them, right? Now that force will pull the heavier elements, the heavier components of the mixture towards the outside, pulls the heaviest elements of that mixture towards outside, and the lower weight ones will remain in the test tube, and hence you will see you have separated the mixture. So what happens? There is this mixture. What am I making? There is this mixture, right? And this is a test tube. It's rotating. Force is acting outwards, and there was this whole mixture in it, right? But after you have applied this force, what happens? All the heavier particles, they accumulate on the outside, and then you see a mixture here, and you will see that they have separated the small particles that you could not filter out with centrifugation. Okay, this process involves spinning a mixture in a tube at high speed. Using centrifugation, the tube becomes horizontal, okay, and the centrifugal force, the force that is acting outwards, we studied in physics, right? Outward force acting on a body moving in circular motion causes the heavier particles to move outwards, where they settle at the bottom of the tube, while the lighter liquid remains at the top. Now, where is it used? It is used mostly in biology labs to separate out red bloods and plasma, and in many chemical industries also this is used. Okay, we also used to do this in our graduation, in our chemistry labs, right? So we do it to separate red blood cells from our plasma mostly. Okay. Now, we saw one more thing, that is coagulation. Now, what is coagulation? Ma'am, coagulation is what happens, there are some substances, again, there are some substances, and they are suspended in the molecules. They are suspended in this solution. So what happens? We use a substance called alum, and we call it fitkadi. It's actually very good for your skin as well, people say, right? So it's mostly used to filter the water. It's crystalline chemical substance used in water purification, to purify the water. Now, this alum causes fine suspended particles to clump together. What happens when you put, it's like a soap something, but it looks like rock, but in the shop you can get it in any provisional store, right? Just go and ask them for fitkadi or alum, they'll give you. Now, mostly people, older people used to tell to put it in your water while bathing, because it's a water purification substance, right? Now what it does, if you keep it in that water for some time, it makes the suspended particles clump together. It forms bigger clumps. Now it got heavier, right? So by just under the force of gravity, it comes down, it suspends down in the solution. So if you put alum, all these will form big chunks in the solution, and after some time you will see these big chunks are now settled down and your water is cleaned. Done? So causes the fine suspended particles to clump together. This process is called coagulation, and the alum is used to act as a coagulant. This alum is called coagulant. These larger clumps thus formed settle by gravity, sedimentation which is called, and this can be separated using water by desalination or filtration. Of course, if these are bigger, they will now can be filtered together. Okay, the formation of cheese from milk. Now, if you ever made paneer or cheese in your home, you'll see what your mother does or what you do is you put some lime water, right? You put some lemon juice inside your milk, and what it does, it makes the milk particles coagulate. A bigger lumps start to form, right? And then we soak out all the water, and a bigger lump, that is your paneer, is formed, that we all love to eat, majority of the people. Okay, so it causes coagulation, and hence it is also being used in our daily life. Done? Now bacha, I think all that is over, and that is it for this whole chapter. I guess this whole chapter has been completed in a very good time. This is all we did numericals. Okay, we understood all the separation techniques. Now I want you to come and join the live sessions, because we will be doing lots of questions, MCQs, numericals. This chapter has lots of numericals. Okay, so make sure you subscribe this channel and join the WhatsApp channel. The link is below, and also you will get the PDF down below. So make sure you subscribe this channel. Okay, bye bye, tata.